Hi, I'm Nick Tusay. I am a finishing graduate student at the Penn State University. Note that that is a, yeah, where's the laser here? That is a Nittany lion, not an O. Don't believe everything you read. So, I kind of want to bring this full circle, or at least try to relate a little bit to what Jesse first talked about. I'm an observer, and I'm here to give you, or to show you some results that really ask more questions than they provide answers. But they're really interesting results. And so like Eric just said, I want to discuss a really interesting subclass of USPs that are disintegrating exoplanets. And that, typically that can tell us a little bit about planet formation from exoplanets. Typically, planets keep their insides on the inside, but these like to put their insides on the outside, and we can study them. All right, so I have a lot to get to, so I'm going to have to rush through a lot of this, so please bear with me. But I'm going to talk about K2-22b. And just to familiarize everybody with that, this is a snippet of the light curve from K2 showing the transits of K2-22b. Those of us familiar with light curves will notice that this looks weird. Right? We have a lot of transits that are extremely variable, going from 0 to about 1.3% transit depth every 9 hours, as indicated by the vertical teal lines at the top. There's enough of these, and they are sufficiently random that we think that they are all connected to the same object. And when you average all these transits together, it looks something like this. You get a somewhat asymmetric transit shape with pre and post transit bumps. And all of this together fits very neatly with the disintegrating exoplanet hypothesis, which goes something like this. The planet is orbiting so close to its host star, it's not getting tidally disrupted, but it is receiving so much radiation on the surface that a large pool of magma has formed on the substellar point that is deep enough to convect with interior layers. And then that mixed surface material sublimates off the surface, goes out into space, condenses into dust particles, and then the dust and gas basically shrouds the planet's surface from incoming radiation. As that thickens up, the surface cools a little bit, turns off the vaporization process. Meanwhile, stellar wind and stellar radiation continue to bombard the shroud around the planet, pushing that into a trailing dust tail, re-exposing the surface to more radiation, heating back up the surface, and beginning the vaporization process anew. And all of that happens on a very short time scale, over 9 hours or less, in a very stochastic and chaotic way. Cool. So, I think it's pretty obvious why we want to point JWST at this thing, and so we did. Great. So we tried to get about 20 hours of JWST time in a cycle 2 program. So we got about that, and we tried to get simultaneous ground-based coverage as well. So we got 4 observations, 4 transits, 2 of which were in a full phase curve. The idea there is, right, this thing goes from 0 to 1.3%, so we wanted to make sure that we would capture about 0.5 to 1% cumulative transit depth in order to try and distinguish some of the compounds in the spectrum that would be produced from the transmission spectrum. Ground is difficult, is the summary of this slide, and KIOPS was fortunately able to give us full simultaneous coverage. Cool. Okay, so going observation by observation now. This is the light curve from the very first observation, full data in the background, binned up in the teal points in the foreground, very simple model, transit model in red, and this shows that for the first observation, there doesn't really seem to be a detectable transit. Okay, variable target, not a big deal. Let's check out the next one. Again, nothing, not great, but you know what? These are the 2 individual transits. Not a big deal. We got the full phase curve. It's going to be awesome. Let's check the first half of the full phase curve. This is where I started to panic. because I do need to defend in August. But luckily, so for those who aren't laughing, this shows nothing again. Luckily, in the second half of the fold phase curve and the fourth transit, we do see a measurable transit, which is great. Thank God. Unfortunately, it is significantly shallower than we had anticipated and hoped, at about 0.16%. This is significantly shallower than the 0.5 to 1% cumulative depth that we were hoping for. It is, however, still measurable. JWST is awesome, and so we can proceed with our analysis. Like I said, we did get simultaneous coverage with KIOPS, which is great, but this is a really faint object, is the bottom line. I can go into more details, but I don't have time, so great. I fit a model to the light curve, and then I fit that transit model to all the Mary spectral channels to produce the first spectrum of the transiting effluence of a rocky planet around a main sequence star, we think. And here it is. Pretty. No oohs and ahs? Okay, great. The unbinned data is in the background, binned up in constant spectral resolution of 17 in the foreground in a pretty rainbow color pattern. And the KIOPS photometry is binned up there as well. Large uncertainties, but it does at least tell us that large optical depth at the same time is unlikely. This is, again, just for that one transit. Yeah. Okay, cool. So the name of the game, right, is to try and understand what the actual constituents of this cloud are based on the spectrum. The data points are pretty to look at, but we want to be able to back that out. So we had a suite of models representing different planetary layers that we wanted to test for in this spectrum, and well, these uncertainties are not great, but we can say some things. First of all, we don't think that this is consistent with an iron, just a bare iron core, right? Some of the ideas is that this thing has just been disintegrating for so long, all of the material sloughed off, and you're just left with an iron core. We don't think that our spectrum is consistent with that. So we think that there's some meat left on the bone, so to speak. Mantle mineralogy is a lot more difficult, especially at the higher wavelengths, where a lot of the subtle differences are important, where, of course, our uncertainties get rather large. But there's something that we hadn't really accounted for. Right here, at the short wavelengths, we see a really interesting sharp feature. We see a lot of transparency and a lot of opacity, and all of our solid dust models cut right through that. So what could that be? Well, short answer is probably gas. We turned to the DACE database and we looked at obvious rock vapor stuff. Short answer, to make a long story short, MgO and SiO should be pretty obvious in this case. However, the opacity or the opacity features don't seem to line up with our data. More info on that in the question and answer section, I'm sure. So then we expanded our search of gases that could explain, or that could be consistent with a small planetary body in a system to include ice vapors. And long story short, we think that our data is consistent with CO2 and NO. Note that I am saying consistent with and not saying definitely detected. That's important for the reviewer. Okay, so, but what does this mean, right? Why are we seeing NO and CO2 on a rocky body that is 3 stellar radii away from its host star? Seems unlikely. I agree. But that's why I'm an observer, and I have brought you questions. That's a good one. Great, moving on. So, in conclusion, I've ripped through this faster than I expected, but there'll be plenty of time for discussion. There's some really interesting and unexpected features in our spectrum, which is cool. So we think we're not seeing a bare core. We think that the long wavelength features are consistent with some kind of mantle-like mineralogy. We'd really like to go back and pin that down with more signal to noise. And then there's these really interesting, weird short wavelength features that, again, we would like to go back and confirm. So I think what this study gives us, besides just questions and confusion, is a really great new way to probe the interior of planets, right? And if we just had a little bit more signal to noise, we could really nail this thing down. And gotcha. Luckily, and so there's two ways to do that, right? Either we go back at this thing and hope we get lucky, or we just go back at this thing and just hammer the crap out of it, and eventually we'll get the signal that we want. Or we try and find something that's a little bit better. Since I have time for it, I'll bring it up. This is the new TESS new disintegrating planet that was found with TESS, BD05 and a bunch of numbers. And we got a cycle 4 JWST proposal to program to study this. And just to be complete with some themes, if you ask when this will happen, it's October. I don't know about 3rd, but it's in October. These observations should happen. Okay, I'll take questions now. I'll stop.
Thank you, Nick. I want to ask the first question because I'm very intrigued. So this CO2 and the other gas you found, could it be the gas that is dissolved in the lava and being released? Would that be creating sufficient optical depth for you to see it?
Maybe. So that's one of the things that we have fleshed out in our discussion. So note that the archive link takes you to the paper that's up on archive that is the first draft. We've significantly fleshed out the discussion in the second draft that's not up yet, waiting for the reviewer to finish eviscerating us. But yeah, there is the possibility that CO2 and NO are released volatiles of disintegrating various materials. Can it produce that much opacity? I'm not sure. Is the answer? Because part of the problem is that we really don't know how much silicate there is, and so is it really just is it a lot of silicate and just this tiny little feature of gas, or is it a little bit of silicate and much more gas? It's really hard to tell with this level of uncertainties. And so, because the uncertainties were so large, I don't trust the retrieval code that I had set up to really nail this thing down with. So I don't know is the answer. All right.
Hi, really cool stuff. Thanks for the great talk. I was wondering for your like dusty models and also like the iron and FEO cases, what goes into those opacities, and do you constrain like grain sizes or any other properties and things like that?
Yeah, so that was one of the things that I skipped over for time. I thought I would need more time, but yeah. So it's we assume me-scattering, and we have a really cool code that basically calculates the opacities from the optical constants, and we assume a grain size distribution of I think it's an effective grain size of 1 micron, which is consistent both with our results and previous results. I did test smaller grain sizes, which gave us unreasonably large opacities. So that is the answer.
Hello, excellent talk. I really like this topic of observations. It's really interesting. I want to ask, can you make comments about, you showed this similar, the second observation with TESS of the tail that develops around the closing planet as it's being, that tail. Could you make a comment of what's the final fate of that tail? Would it stay on that orbit, or does the stellar wind would have an effect on it eventually distributing through the inner region, or what happens with those minerals there?
Good question. I am honestly not sure how much of this flows in and gets blown out. The way that the leading tail comes about is because some of the as the dust comes off the surface and forms the cloud, that gets pushed into a trailing tail, but some of that dust is able to survive long enough with a low enough beta to fall into a closer in orbit and then proceed into the leading tail. And so the trailing tail generally gets blown out and thinned out, but then this one is so active that it's just getting replenished all the time. And so to us, it basically looks pretty static. Yeah.
Okay.
Yeah.
Artem Yushin from UC Santa Cruz. So I'm wondering, when you're fitting your spectra with opacities, do you have like an underlying model that provides you?
Oh.
No, for the
You
other
said
one.
when? Sorry. Go ahead.
Do you have an underlying model that gives you some abundances, or is it just fading the opacity to some amplitude?
Are you talking about the gas or the dust?
The gas.
The gas? No, I don't know, because part of the problem is that I am not sure how to estimate the gas abundance in the cloud, because I'm not sure where that gas is. I don't think it's fair to assume hydrostatic equilibrium in this case, and I don't really know where in the cloud it is. And so, if I had stronger measurements on the silicates and could confidently pin down abundances for those, then I could at least estimate how much leftover stuff is gas, and then from that maybe begin to say something. But I don't, so I don't know. But I'm happy to, if somebody has ideas.
Like you don't have volume mixing ratios anywhere in that fit?
No.
Okay. Good luck
All
with
right.
the defense.
Thank you. We're slightly over time. Let's thank Nick and all the speakers again.